Chapter 8.4, Scientific Notation. I'm sure you guys have used it in science class, probably used it in math class before. So the first question is, why is scientific notation helpful? When do we use it? And we normally use it with very large numbers or very small numbers. So for instance, for measuring the distance to the moon, we could write that as 238,900 miles, or we could write it as 2.3 times 10 to the 5 miles. That would be scientific notation. The same distance to the sun, 92.96 million miles. We could write that instead in scientific notation as 9.2 times 10 to the 7 miles. So the benefit here, notice, is that we have it in the same format, right? We have these two very different distances. But now we can really easily compare them. And you can imagine something where you had more zeros, right? Let's say you had 100 zeros. It'd be really difficult to sort of make sense of that. And so scientific notation helps us make sense of these very large numbers. And the same is true for very small numbers, right? So here we have an atom. The radius of the atom is 0.0000000000053 meters across. And when you see that, that is impossible to immediately make sense of. Because the first thing you actually have to do is think, how many zeros are there? You'd actually have to count it, right? And so imagine you're reading that like in a scientific text, and you had to stop and count them. And imagine there was another number where there was like one less zero, but you couldn't tell that at a glance. So you were thinking you were looking at the two same things, but you really weren't. And again, that's why we use scientific notation. We could write that as 5.3 times 10 to the negative 11 meters. So notice two things. One, the negative 11. So when we have these smaller numbers, we're going to use negative exponents, because negative exponents, we learned yesterday, is really a form of division. Okay, but the second thing is this, and the more important thing is this. Math is a language, just like English, anything else. And the point of this language is to help us explain our world, our universe together from one person to the next, right? And so we want that language to be as clear and concise as possible, as easy to share as possible. And this is really easy to digest, whereas this was really difficult for us to make sense of. And that's why we use it. All right, how do we write scientific notation? Well, it's always some coefficient, in this case 2.5, and it has to be between 1 and 10, not including 10. So 2.5, 9.2, 9.34, whatever, between 1 and 10. And then times 10 to some exponent, right? And that exponent has to be an integer, so it could be positive or negative, but it can't be a decimal, it can't be 5.2, it has to be 5 or negative 5, 6 or negative 6 or something like that. All right. So now the question is, what exponent are we going to use? So quickly what we're going to do is we're going to review multiplying by 10 and then dividing by 10, or multiples of 10, and then seeing how many we need, right? So what happens when we multiply by 10? Well, decimal place moves 1 to the right. We end up with 102. When we multiply by 100, the decimal place moves 2 to the right, and we end up with 314. Times 1,000, 3 zeros, move 3 spaces to the right, 1, 2, 3, and we end up with 5,685. Keep in mind, times 10. 10 is, we could think of as 10 to the 1. Times 100, we could think of as 10 squared, right? 10 times 10, 2 zeros, 100. 1,000 is 10 to the third, right? 10 times 10 times 10, 3 zeros, 10 to the third. So that's how we're making the leap between multiplying by powers of 10 and then writing it in scientific notation. So the key takeaway, right? When we multiply by a power of 10, we move the decimal place to the right. And this exponent is going to tell us how many spaces to the right. Division. Divide by 1, nothing happens, right? That stays 265,800. But we divide by 10, we move 1 space to the left. We end up with 26580, and our comma moves 1 to the left as well. Divide by 100, right? We're moving 2 to the left, right? And notice, again, we're dividing, so we're moving to the left. The number is getting smaller. So 26580, and our decimal place is right there. So the comma moves 1 to the left again. Divide by 1,000. We're moving 3 decimal places to the left. 1, 2, 3, right there. So we end up with 265.8. And again, dividing by 10, right? We divided, we can think about this too. We divided by 10 to the 1. 100, well, we divided by 10 squared. And 1,000, that's like dividing by 10 to the third. Now, here's the thing. We learned yesterday that we could think of as division as the inverse of multiplication, right? So dividing by 10 to the 1 is the same as multiplying by 10 to the negative 1. Dividing by 10 squared is the same as multiplying by 10 to the negative 2. And dividing by 10 to the third is the same as multiplying by 10 to the negative third. And so that's where the negative exponents come in, right? It's when we're trying to divide. How do we express division in scientific notation? And it's by using the negative exponents. So the key takeaway, when we divide by a power of 10, we move the decimal place to the left. And the exponent tells us how many spaces to move. All right. First set, let's write these numbers in scientific notation. Remember, our first goal is we need a coefficient between 1 and 10. 9.2 already done, so I'm just going to write 9.2. But I got to write times 10 to something. But I don't want to actually move the decimal place, right? I don't want to move 1, 2. I don't want to move at all. I want to move 0 places. So I'll just write 0 places to the 0 power. And remember, anything to the 0 power, right, is just 1. So this is like saying 9.2 times 1, which is just 9.2. And so that's why that works. Okay, so that's sort of a tricky one to start out with, but it makes sense, right? We want to move 0 places, so it's a 0 power. Okay, 874.3. Well, I got to make that coefficient between 1 and 10. So it can't be 0.8. It can't be 87.4. It has to be 8.743, right? The decimal place has to go between the 8 and the 7. So now the question is, what power would we need to move it back to where it is between the 4 and the 3, right? And that would be 1, 2 to get it back there. So that would be 2. We would have to multiply that. We'd have to move it twice to the right. And so we're moving it 2 spaces times 10 to the second power. All right, 0.0032, right? The only place where I can write, that has to be 3.2. Right, it can't be 0.3 or 0.03 or 32. It has to be between 1 and 10, so it's 3.2. And now the question is times 10 to what power? So think about it. We need to get that. We're right here now. We're at 3.2. We need to move it back. How would we move it back to where it originally was? It would be 1, 2, 3 spaces to the left. So the left is division, and we show that with a negative exponent. So it's 3 places to the left to the negative third power. All right. Next, we're doing the opposite. We have numbers in scientific notation. We want to write them in standard form. So just a normal number, right? So 2.4 times 10 to the fourth. So this is telling us we need to move the decimal place to the right 4 spaces. So 1, 2, 3, 4. It's right there. Just fill in the zeros and you get 24,000. Next. 2.4 times 10 to the negative 3. So we still have 2.4. But they're saying move 3 places to the left. So 1, 2, 3. This is where our decimal place goes. Fill in our zeros. And we end up with 0.0024. And if you wanted to write that 0 in front, you can. It doesn't make any difference to the number. And that would be standard form. Finally, 2.4 times 10 to the 0. Well, this is another trick, right? So remember 10 to the 0. Anything 0 is just 1. So that's just 2.4 times 1, which is just 2.4. Nothing changes there. That's your standard form. All right. One of the things that scientific notation is really helpful for is ranking numbers from least to greatest, because it makes it really easy to compare. So we're just going to write these 3 numbers in scientific notation, and then we can just rank them, biggest to smallest, right? So 65 million, I got to write that. Well, that's 6.5. I know that's my coefficient. And then times 10 to what power? So how would how many spaces am I moving? Well, 6.5 is right there. So I had to go 1, 2, 3, 4, 5, 6, 7. I moved 7, right? Times 10 to the 7th. Okay? And then the next 2 are actually already in scientific notation, so that makes it really easy. Times 10 to the 6th, and then 2.4 times 10 to the 7th. Okay, so I'm going to go to the side and do a little thing here to just show you. We already know which one's the smallest, okay? Think about it. If you have 100 and then you have 20, even though 2 is bigger than 1, it doesn't matter because you have this 1 is in a greater place, right? It's in the hundreds place instead of the tens place. So if you have more zeros, think about that. If you have more places, it's bigger than any number with fewer places than it, place values. It doesn't matter what that first number is in that case. So if we look over here, we're moving 7 places over here and 7 places over here, and then 6. So we know that the first number and the third number are going to be bigger than this middle number. We know that this has to be the smallest. And notice I did not even look at the coefficient yet. I know first by looking at the exponents that anything to the 7th power has to be bigger than anything to the 6th power. Okay, now, so we know that's the smallest. Now the question is, which one's bigger, the first or the third? So now I'm just looking at these, right? And so now we're both multiplying by 10 to the 7th power. So now we're going to look at the bases, the coefficients. 6.5 is bigger than 2.4, so that's the largest, right? The largest, the biggest, and that means this is the middle number. Okay, so quick recap. We first looked at the exponents. The bigger exponent means it has more places, more zeros. It has to be bigger. Just like 100 is bigger than 20, even though 1 is smaller than 2, right? Then, once you rank them by the number, like the power, then you can look at the coefficient. 6.5 is bigger than 2.4, and then so that's your second step.